The talk is basically based on the extension of the conventional real as well as PT symmetric potential. And actually, this is the extension is possible only after the discovery of two new orthogonal polynomials. As we know, the orthogonal polynomials plays important role while we solve this Schrodinger equation or for any non-potential problems. So after the discovery of new polynomials, most of the potentials are extended rationally and reduce the solutions of these potentials in terms of exceptional orthogonal polynomials. These new polynomials are also known as exceptional orthogonal polynomials. So here in this talk, I will discuss the sum of extension of the real and PT symmetric complex potentials. So please next slide. Yeah. First, I will discuss about basics about exceptional orthogonal polynomials. I'm not going to discuss the details. And then I will consider some examples of the real potential as well as PT symmetric complex potentials. In the PT symmetric case, I will consider one body system as well as three body system also. I have done on higher body systems also, but in this talk, I will consider only on one body and a three body system. And then I will summarize our talk. So next, please. Yeah. In general, the extended potential looks like this type of equation number one, which is nothing but the sum of two terms. One is conventional one, V of conventional. Conventional means with that's potential we have already. Conventional means the potential which we have the solutions already, and the non-potentials like harmonic oscillator, radial oscillator, SCAF2, Cauchy-Taylor, Coulomb, Morse, Rosen-Morse. These are conventional potentials which we have. And there's one rational term. This rational term is in the form of this P by Q form, and that's we have to find out the rational term. And people have found out the rational term V of X for most of the conventional potentials. And after the solution of these extended potentials and found the solutions in terms of newly discovered exceptional orthogonal polynomials, and the well-known these polynomials are exceptional Lagrange and the exceptional Jacobi polynomials. And the interesting thing is that the energy eigenvalues of these polynomials, these potentials, extended potentials, are same as the conventional one, but the wave functions are completely different. Which are written in the form of exceptional polynomials. So let's discuss about the exceptional orthogonal polynomials. As we know, the second order differential equations, which are generally satisfied by the orthogonal polynomials. So for the exceptional cases, the differential equation looks like same, except here you have Pmx and another function Q of Nmx. Here P also depends on integer m, which is 0, 1 to any value. And n we know already, this is equivalent to eigenvalue problem. So n gives the eigenvalue related quantity. And Q as a function which depends on both n and m, both. And in the normal second order differential equation, which depends only on n. But in this case, we consider this type of differential equation which depends on n and m both. And it has been shown that for the particular case, if we put m equal to 0, these functions p of mx and q of nmx reduce to the normal function p of x and q of nx, which are suitable for the conventional polynomials. And for m is greater than 1 or equal to 1, these the solutions of this type of differential equations are generally known as x1 type polynomials, x2 type polynomials, and more general the xm, exceptional orthogonal polynomials. So this is a more general type of exceptional polynomials. And the normal usual or conventional polynomials which we have already is one of the special case of these polynomials. Okay, so next please. Okay, so let's discuss the Lagrange type of exceptional polynomials. In this case, here we can see this these two functions, p of mx and q of nmx. In the equation 4, this function p of mx, which depends on normal Lagrange polynomial also. If you put here m equal to 0, say m equal to 0, the second term vanishes, and we get p of fx equal to alpha plus 1 minus x by x, which is true for the normal Lagrange differential equation. And similarly for q of nmx, second function, equation 5, if you put m equal to 0, we get simply n by x. That's also equivalent to the normal Lagrange differential equation. And and the solution for this type of, if you consider the Lagrange case, so the solution looks like, yeah, please next slide. Yeah, solution of this differential equation looks like this. In terms of the combination of the normal usual Lagrange polynomials, we can see here so many terms. There is some usual Lagrange polynomials, and if we put m equal to 0, m equal to 0, we can easily recover the usual Lagrange polynomials. So this is more general, and this type of polynomial is generally known as exceptional orthogonal Lagrange polynomials. So yeah, next please. Yeah, next slide please. Yeah, and the weight factor and the norm related to these polynomials are also get modified. The weight factor looks like the equation number 7, which is there is some numerator term which is also present in the normal Lagrange polynomial, and there is a denominator term lm alpha minus 1, and if you put it here m equal to 0, we get the normal Lagrange polynomial, and for m equal to 1, that's equivalent to the x1, m equal to 2, the x2 case, and so on. So, and the norm of these exceptional Lagrange polynomials are defined like this equation 8, and this also depends on m. So we can check for m equal to 0 here, and this is equivalent to the normal Lagrange polynomial. So this is a more general result for the Lagrange polynomial. So that's the due to this special feature we call this exceptional Lagrange polynomials. Okay, next please. Similar to that Lagrange case, here we consider the Jacobi case also. In this case, again, we have defined this P of mx and Q of nmx like this. I think this is a little bit complicated term, but we can easily reduce this in the form of normal case just by putting m equal to 0 here. We can see P of 0 equal to nothing but the last two term, minus alpha plus 1 by 1 minus x and beta plus 1 by 1 plus x, which is equivalent to the normal Jacobi polynomials. And for any value m is greater than or equal to n, we get the exceptional orthogonal polynomials. Similarly, for the second function q of nmx, here we can easily obtain the terms related to the normal Jacobi polynomials after putting m equal to 0. And that's equivalent to, if you put m equal to 0, we get the first term vanish, p of m minus 1, so that's vanish. And we get the term which depends only on n, alpha and beta. There is no m for m equal to 0. So and for m equal to higher value, m is greater than equal to 1, and that's suitable for the exceptional polynomials. And in this case also, we can see here the weight factor. Yeah, next slide please. In this case also, the weight factor and the norm of these polynomials, Jacobi polynomials, are also modified. Yeah, next slide please. Yeah, and the solutions of these polynomials looks like this. This is nothing but the combination of the usual Jacobi polynomials, which depends on n and m, and the solution looks like this. Yeah, next slide please. Yeah, weight factor similar to the exceptional Lagrange case. In this case also, the weight factor gets modified, and there is extra term PM normal Jacobi polynomial case, and we can easily recover the here. And similarly, in the norm, we can get the constant term here, the normalization constant C, M, and alpha, beta, which depends on both N and M. And if you put M equal to 0, we get the usual, we get the constant related to the usual Jacobi polynomials. So if you now the properties or the different properties related to these polynomials, we can try to get the rational extension, and people have found the different potentials which are rational extension of the conventional one. So let's go to the next page, please. Yeah, so now let's come to the rationally extended potentials. Generally, these potentials are obtained by different approaches, such as supersymmetry is one of the strong approach to get this type of potentials. Or some people also call this Sushi approach as pre-potential approach. Just both are equivalent. In Sushi approach, we define the super potential, but in pre-potential approach, they just other nomenclature like pre-potential type of term, there is some function type. So these two are equivalent, and another method is Darboux-Beckland transformation. And group theoretic also obtained these potentials using this potential algebra approach. And the simplest method is the PCT approach, but not a single method is I think sufficient to get the extension of all these potentials. So for the different potentials, we can apply our different potentials. For the different potentials, the different methods may be required to get the rational extension. So the simplest one is the PCT approach, and the most general one is the DBT approach. So we can use DBT approach to get the rationally extended potential. And what we have seen, some of the potentials are even rational potentials are not in the form of these EOPs, and these potentials are like Morse, Rosen Morse, and Coulomb potentials, etc. And the solution of these potentials are something different, which are also combination of the normal Jacobi or Lagrange polynomials, but not in the exact form of these exceptional orthogonal polynomials. And similarly, some of the real potentials also, which are not possible to extend rationally, like real SCAV2, there is due to the presence of the singularity. So, but the PT symmetric extension are possible for this potential. So, people have applied these approaches and obtained number of rationally extended potentials, even real as well as PT symmetric. Yeah, next please. Yeah, let's consider some examples here. We have considered only one or two examples of these real cases, and not going to discuss in detail the solution of all these potentials. Then I will come to the PT symmetric case. So first of all, in 2008, just after the discovery of these two polynomials, Kushner et al. Found the rational extension of radial oscillator case, three-dimensional oscillator case, and often this rational term P by Q like this, which is highlighted with red, equation 14. We have the first term, conventional potential we have already, and they found this extra term for omega by omega r square plus 12 plus 1 minus 8 omega 12 plus 1 by omega r square term. And often the solution of this type of potential, and so on, the solution can be reduced in terms of exceptional Lagrange polynomials, and the solution of this potential is given by equation 15, and which is for the x1 case. So the exceptional Lagrange polynomial like L n plus 1, and they have also shown these potentials, as we know, the conventional potential, the radial oscillator conventional potentials are supersymmetrically shape invariant. This is a property in the supersymmetric quantum mechanics. Shape invariant is one of the important properties. And they have also shown these potentials, the extended radial oscillator potential are also shape invariant. Okay. So now, yeah, next please. Similar to the X1 case, later on, the Sasaki et al., they have extended these potentials to the X2 and higher, more general, the XM case. And the terms looking some complicated here. And the extended potentials here, which is now M dependent. And the conventional one is the same, V of conventional R. And the other extra term, which are written in the form of P by Q, and these are the rational term. And if you put, the interesting thing is what, if you put M equal to 0 here, if you put M equal to 0, we can recover the conventional potential. So this is the more general potential, extended potential. And the solution of this one is also in terms of now XM exceptional Lagrange polynomials. So we can easily see here equation 17, the Lagrange polynomial, exceptional orthogonal Lagrange polynomial. And for the M equal to 1, we get the X1 case, and M equal to 0, we get the conventional case. Yeah, next page, please. Yeah, similarly, I'm not going to consider the X1 case now for the scarf one, just I'm considering here for the showing the importance of the exceptional Jacobi case here. So we have considered this example, the scarf one case. So we have the conventional potential, scarf one potential. This is trigonometric scarf also, and that is sec10 potential, sec square x, and sec10 potential. And the rational term of this potential is defined like this: V of M rational, and this is given in terms of usual Jacobi polynomial. And the solution of this extended potential are given in terms of exceptional XM Jacobi polynomials. And this extended potential, the scarf one, is also shape invariant. Yeah. So next one. Yeah, this one is the generalized positron potential, which I've also extended rationally and obtained the solutions in terms of exceptional Jacobi polynomial, similar to the scarf one case. These potentials are also, and all these potentials we have obtained also through the group theoretic approach. The same potentials we have obtained through a group theoretic approach. Yeah, next page, please. Yeah, now come to the PT symmetric complex potential. Yeah, we have the well-known, the SCARF2 potentials, which is well-known, and there is so many applications of these potentials. People are working on these potentials, SCARF2 potential. The conventional potentials we have like this. There is the minus b square minus a plus 1 sec hyperbolic square plus this I of b term. Here b goes to ib, and 2a plus 1 sec hyperbolic s and 10x. Under PT symmetric transformation, here we get I goes to minus I, and 10 hyperbolic x goes to minus 10 hyperbolic. So this is the PT symmetric potential. And the bound state energy eigenvalues we have already, equation 22, which is En equal to minus a minus n square. And the solution of this potential is also well known and written in the form of normal Jacobi polynomials P of n alpha beta, which is given by equation 23. Now we consider the scattering state solution of this potential, which is also available. Yeah, please next page. Yeah. So if you consider the scattering state solutions, for the PT symmetric case, we have the transmission amplitude, left and right transmission, and similarly for the left and right reflection. So we have considered for the, this is the conventional potential. So the results are well known. So just we summarize here for the sake of simplicity while when I will discuss the extended case. So yeah, next page, please. Yeah, for this one is for yeah, reflection amplitude R, and here we have seen this conventional potential shows the handedness properties, which is one of the important properties for the PT symmetric potential. So here we have seen the transmission and reflection amplitude for
Rajesh?
Yeah, sir.
Yeah. Sorry, actually we are running very late.
Yeah,
So
yeah,
can
only
you...
sir, only 3 or 4 minutes now.
Okay.
Yeah.
Okay. Yeah. Yeah.
Okay, sir. Okay,
Thank
okay.
you.
Yeah,
Thank you.
next please. Yeah. Next slide. Yeah. Now this one is the rational extension of the PT symmetric SCARP2, which is obtained by Midya and Barnard, and the expression looks like this in terms of the exceptional Jacobi polynomial. The solution is also given here in the equation 28. Yeah. When we consider the scattering state solution, which we have obtained, the scattering state solution of this extended potential, we get the transmission and reflection amplitude like, which is now M dependent. Yeah. Yeah, please, next slide, please. Yeah, this is I think a little bit complicated, but it's very we can see here this is more general. Now T and R both are depends on M, and if you put M equal to 0, we recover the result corresponding to the conventional one. So this is more general result, and we can easily see the all the properties which are satisfied by the conventional one, this is also satisfied by the rationally extended one. Yeah, next slide, please. Yeah, the one of the most important problem, that the three body problem. Calogero first considered this constructed this problem, three body problem, by considering two terms. Generally, they define V of C with the harmonic and inverse square potential term, and these two terms are defined by equation 33, and they solve this type of potential. Okay, yeah, next please, next slide. Yeah, they solve this type of potentials by defining the Jacobi coordinates and reduce this problem in the polar coordinate form by defining x is equal to rho sine phi and y equal to rho cos phi, and the rho which we have already, equation 34. Yeah, next please. And then using the method of separation of variable, they decouple that Schrodinger equation in two independent equations. So one depends on rho and another one depends on phi, and obtain the solutions exactly. Yeah, next please. Yeah, thereafter Wolfage, they also defined some complicated type of interaction term. So this is actually three body problem. So V of W, one more interaction term they have defined here, x1 plus x2 minus 2x3, and the rest two terms are just a cyclic permutation of the first one. And solve this problem. Either we can solve this problem with or without the inverse square potential. And thereafter, Khare and Bhaduri, they again define some more new interaction term. Yeah, next please. Yeah, V of interaction. They have considered these type of interactions, A, B, C, and D. There are so many interaction terms, and in the A and B, these two are real, and C and D, we have made this complex term by replacing F1 with IF1 and complex and PT symmetric. So now these are the three body problems which are already known, and now we have extended these problems by defining some more interaction terms. So please next. Yeah, here in the last two terms, V of rational 1 and V of rational 2, we have added these two interaction term, and the form of these two interaction term looks like 41 and 42 equation number, and the 41 we have defined. Let's fix the 41 V operational 1 interaction term, and in the 42 V operational 2 interaction term, we have a number of options. We have xi x, so we define this xi of x. We have different possibilities of xi of x, and for the different possibilities we can find the different rational potentials. So here we consider only the x1 case. I'm not going to consider the xm case. So we consider here only the x1 case. So please, next please. Yeah, we have the different form of this Jai. First A and first B. Actually, we have the different Jai, but we have the same potential. So when we solve these two interaction term, we get the same potential. Similarly, second form, we have two different form for the second one, 2A and 2B. But when we solve these two also, we get the same potential. We have different interaction term, but the potentials are same. That's very interesting. So now, yeah, next please. Similarly, we have two different interaction term, third A and third B, but the same potentials with the same solutions also. And fourth one is also something different, and x1 minus x2 by some denominator with cyclic permutation term. Yeah, next please. Yeah, now we just now here we consider the PT symmetric case only. So consider the terms with IF1 and try to find the solution of this type of interaction. And here we have considered the Xi equal to 1 by 3 root 3 x1 plus x2 minus 2x3. These are generally we get when we define x1, x2, and s3, and then we put some constant term such that we get the exact form of the potential. That's we consider here 1 by 3 root 3, and the cyclic permutation term here we have. Yeah, next please. Yeah, so in that case, we have changed only the phi term, and there is no change in the rho term because the solution of the rho term is related to the Lagrange case, and that's equivalent to the oscillator problem. So we generally, whatever terms we have considered here, that's related to the phi term now. So we define the phi term here, and after solving that three body problems, we get the more simplest form of this potential, equation 48. That's the more simple, that's equivalent to just similar to the Eckart potential. And the rational term is also obtained and given by 49, and that's the rationally extended Eckart actually, which is already obtained by Kushner. But when in that work we put some complex parameter, or when we put or replace some potential parameter with the I, some here we have f1 only, and we replace that I f1, then we get the PT symmetric case. Yeah, next please. Yeah, now the complete potential looks like this one. This is the x1 case only, not xm case. We have also obtained the xm case. So this is the x1 case, and this potential is PT symmetric. Here the phi under PT transformation, phi goes to pi plus phi, and t goes to minus t, and I goes to minus I. And so under this transformation, the potential is PT symmetric. Yeah, next please. And the solution also looks like in the form of y of L. This is not the exact form of the exceptional Jacobi polynomials, but there is some new type of polynomial, y of L, and this y of L can also be written in the form of normal Jacobi polynomials 52. But the potential is well defined, and rational extension, there is no any type of singularity in this potential. So the potential is well defined. Yeah. So this is the solution of this potential, which is not in the form of exact form of the exceptional Jacobi polynomial. Yeah, please next. And these are the parameters and energy eigenvalues, so doesn't matter. Yeah, next please. So that's the problem. We have only considered up to the x1 case for the three body problem. Xm case is I think there is only calculations. So now we summarize our talk. So first we have consider the differential equations related with the EOPs and discuss their solution in terms of x1 and x1 case. And we have also shown that m equal to 0, we recover the usual cases. And we consider some examples related with the real and PT symmetric case. And the scattering state solution for the PT symmetric SCAP2 potentials are also discussed and shown. These potentials also satisfy the same properties which is already satisfied by the conventional cases. Yeah, next please. And finally, we consider the three body problems and obtain their solutions in terms of X1 Jacobi EOPs. And the solution was not in the exact form of X1 Jacobi, but there was the exact form of X1 Lagrange. So with this summary, I thanks to all of you.
Thanks, Rajesh.
Yeah.
So are there any questions?
Oh,
Okay, so I don't see any questions. So anyway, so thank you, Rajesh, and with this we come to the end of this session. So thank you, everybody, and we will see you at 5 o'clock today for the evening session. Thank you very much.